Welcome to Climate Change, Causes and a Roadmap to a Solution. This is a general audience presentation. If you're highly technical, you feel free to sit in, but it's definitely general audience. This was put together by the MIT Alumni for Climate Action. Our website's listed. I'm John Dobbles, and I'm part of that group. Presentation content, we try to keep it to 45 minutes, but we'll talk about causes of global warming, the historical perspective on the Earth's temperature. Does temperature change really matter? And the pathways to address global warming. We talk about some technical pathways with transportation as an example. Also, education is critical. Some issues and concern with proposed solutions, for example, clean electricity, and how you can help. And there's a personal calculator for carbon footprint. And then there's some follow-on answers and questions you might have. The MIT Alumni for Climate Action, we have a wide range of disciplines. Now, granted, we're more science-based, but it's wide range. Also, wide range of ages and experience. We've taken a very non-partisan approach to the recommendations. Granted, they're science-based, but it's as nonpartisan as you can get, I think. The technology assessment, I've arbitrarily put in 3 buckets. We never formally did this, but if you look at it and you read the document, it's what's available now or in the very near future, what likely technology will be available with some additional development, and that's just like reasonable development. And then there's also this other bucket of possible, but it needs additional and probably significant development. But the goal of all this was to put together an understandable, usable roadmap to solutions to climate change. There are 2 approaches, and I think it is truly binary. You can ignore and do nothing, which some people want to do. I think that's goodbye civilization. The other approach is take meaningful action. And this is the outline of the graphic of the roadmap. And we'll talk more about that in detail as we go through. So, how do we achieve zero carbon emissions by 2050? And the 2050 has been picked because if we don't stop in 2050, it's very hard to meet a 2100 target on certain temperature increases. And so you'll see that as we go through the presentation on how that all weaves together. But if we look at the 2 elements of it, one is the technology. We can pretty much get to 2050 with existing technology. It needs some refinement, but nothing really needs to get invented, as it were, to get there. The second part, though, is the education and adoption. And that's going to be the more difficult path. It's not a very clear path. There are a lot of potential roadblocks, but if we're to get these ideas implemented, education is critical. What are the causes of global warming and what's a solution? Just imagine you go back to 2nd grade class. Mrs. Barnhart happened to be my 2nd grade teacher. So we're having a little dialogue in class, and that goes back and forth, and finally somebody raises her hand and says, "Mrs. Barnhart, how do we stop global warming?" And her response is, "Quit burning stuff." So if you stop listening to the presentation right now and remembered nothing else other than quit burning stuff, you'd have a good understanding of what it takes to address global warming. What are the causes of global warming? Well, a simple explanation is certain gases, carbon dioxide, for example, end up acting like a blanket. And so they trap the heat that would normally escape from the Earth. So right now, we've got more CO2, and that little blanket is becoming more like a down comforter. So we need to reduce the amount of carbon dioxide. What are the sources of CO2? Well, you've probably seen all these before, but clearly burning coal or any fossil fuel, natural gas. The air conditioning, there's some other fluorocarbons that are involved with that, but gasoline, diesel fuel, wood-burning fireplace, and yes, cows emit methane as well. We're not going to talk about cows today, but yes, they are a problem. So what are the various emission sources? If you look on the left-hand side, carbon dioxide is about 80% of the greenhouse gas. Methane is only 10%, but methane is at least 60 times worse than carbon dioxide in terms of its effect on warming the earth. Then you've got some nitrous oxide and then the fluorocarbons that I mentioned. Now, the other thing to remember, not only the gases, but how long do they stick around? So CO2 stays in the atmosphere for 100 years. Now, that's, does deteriorate over time, but just think about that. There's some CO2 from 1950, actually earlier, that's still in the atmosphere, that's still having an effect on warming the earth. Methane's about 12 years. The nitrous oxide's 120 to 125. And the fluorocarbons are about, I put 200 years. It's actually longer than that. But do you want to remember one thing? These gases last a long time. And just think about the 1950 CO2 still being in the atmosphere. Now, does concentration of CO2 vary over time? The answer is yes. So based on ice core samples that have been gathered over time, go to the left-hand side of the chart here and look at, start 500,000 years ago and then see the pattern of CO2 over time. And it's fairly regular, and the top and the bottom are about the same over time. Now, where we are right now, on the right, go to the right-hand side of the chart, it should be peaking, if not starting to trend down. And then look what's happened. It's just skyrocketed. Now, granted, this is compressed, but this is a post-industrial revolution, and you can see where we are in 2021. Now, some people say, well, does CO2, does that really affect the temperature? Here's a chart since 1950, and the blue line is the CO2, which you saw on the previous line. This is stretched out a bit. It was compressed on the other one. And then the red dots represent the temperature of the Earth for a given year. And you can see how they track, just right on top of one another. So, and it's only going to get worse. Whoops, sorry about that. What part of the Earth gets warmer? Well, two things. One is the atmosphere, which we all feel. Another is the oceans. Now, the oceans actually absorb more CO2 than the atmosphere. Unfortunately, when temperatures rise in the ocean, they're able to absorb less, and they actually begin to give up CO2. So, that's been will be a source of CO2 that we didn't anticipate. In addition, the higher water temperature and the increased acidity of the ocean because of the CO2 damage coral reefs and food sources for fish. If you had to look at an ecosystem that's in trouble, the oceans are clearly in trouble. Now, does the Earth's temperature or average temperature really matter? One day it's 20, another day it's 50, another day it's 80. It varies all over the place. Well, the answer is yes. The Earth is more like your body and the temperature matters. The body is an ecosystem, and the temperature range in that ecosystem is very limited. The Earth is very similar to that. And if you think about your body operating out of this very narrow band of temperature, then what you have, you're unable to survive. You get organ damage or die. And that's really, if you think about the Earth, think about your body temperature and that ecosystem. So when the Earth's temperature increases, what happens? Well, I think we've all heard about different weather events. This happens to be billion-dollar weather events in 2021. Now, this is only through September. And you can see that it's all parts of the country, West Coast, East Coast, Upper Midwest, South, everybody's affected. Question is this an aberration or what's happened over time? And so here's the $1 billion weather events since 1980. So we've got 40 years worth of data, little over 40 years worth of data. And you can see these events. Now, these are the dollar amounts are adjusted for inflation, so everything's constant. And you can see the increase over time. The trend line's definitely up, and this is only through early October, so we don't know what's going to happen by the end of the year. But you can clearly, the number of weather events is increasing. Well, how much time before it's too late? We have a few years, 20 years or so to make a decision. And the 2100 goal, as I mentioned, was 1.5 to 2 degrees C, which is 3 to 3.5 F. So the amount of time left or in the CO2 piggy bank, as you were, is bank's almost empty. We need to start making changes now. And what that means is we have a rapid decline in CO2 emissions. The problem with this situation is once you realize you got a problem, it's too late. And people have been talking about this for a long time. But if you say, gee, everybody seems to recognize that the Earth's too warm, it's way too late to change because go back to the CO2. How long does it stay in the atmosphere? 100 years. So how much time is left? Here's a sort of way of looking at it. The amount of CO2 accumulated or emitted over time, how much we do, what's the budget left to get to net zero by 2050, and the current annual output means we're going to exceed our target within 6 years in terms of overall CO2 emissions. So the conclusion is this. It's going to be nearly possible to hold the temperature increase to 1.5 degrees. It's more likely 2.5 to 3 degrees, which is 4.5 to 5 F, even with a major effort. Now, the COP26, which recently concluded, has a number a little bit less than that, but it's a major effort no matter what, even to get to, say, 2.5 to 3 degrees. What happens when the Earth's temperature rises? Well, we talked about the polar ice cap. And then oceans rise, and then that causes more flooding as well as more rain. And it's expected that the oceans will rise about a foot between now and 2100. So if you go to the Outer Banks in North Carolina or Florida or any place and add a foot to the ocean, it takes up a lot of land. In addition, what you have is extreme weather patterns. For example, in British Columbia, they had extreme heat this past summer, in 2021. Record temperatures that dried things out. They had forest fires. Then it turns around, they just had recent record rains in this last few weeks. So you get this wide range of patterns in certain areas, and that's going to affect more and more of the United States and the world over time. Historically, who's contributed most emissions? Well, if you just look at the circles for a second, you got Europe at about 24%, U.S. and Canada at about 27%, and somehow these data were grouped, so this is how we had it. But so Europe and U.S. are about the same. China, roughly half of the U.S. at 13%, and India is very much on the low side historically. Now, what about today? That's a different story today. So on the x-axis, look at it this way. The size of the circle is the amount of the emissions. So China is the biggest emitter at about a little over 10 gigatons a year. U.S. is next, a little over half of that at 5.4 gigatons. And India is at 2.6, 2.7. So that'll give you some relationships. Now, if you look at China and say a lot of the products in China are exported to the U.S., so U.S. imports, that CO2 should go with those imports when you're calculating this. So the U.S. terms of its emissions, is actually higher than what's shown on this chart. Just add the little flag there in the circle, and China is less. An issue now is per capita. So this is how high the circles are. So the U.S. is just about the #1 worldwide per capita. China is much less, and India is much less than that. Both China and India obviously have very large populations. As they continue economic development, per capita, their emissions, based on historical patterns, would increase. So that is a real issue going forward. What are the sectors, primary sectors, uses of emissions? Well, agriculture, about 10%, building and homes, 12%, electricity production, 25%, industry and manufacturing, about 24%, and transportation, 29%. So transportation, industry and manufacturing, and electricity production are all about the same. What are the solutions? How do we really frame the conversation about global warming? I mean, it's a complicated issue. So let's look at it. If we take 3 different categories, the technology, when we talk about it, I think it's fair to say, and I hope that we'll give you a sense of that. By the way, there's a lot more information behind all of what we're presenting today. But if you say the technology, we've made huge progress with known technology, or we can make huge progress toward addressing global warming with existing technology. If we think about the scope and the complexity, think about World War II in terms of how broad it is, the scope of it. It's very complicated, but it's much longer time horizon. That was a fairly short time horizon versus what we need to think about for global warming. The commitment is what's critical, in addition to the other two. But the public commitment has been a major barrier so far to addressing global warming. So how complicated is the solution? Well, you can see that what's coming in is a Rubik's Cube. So if you think about Rubik's Cube, it's a multi-dimensional problem, and with a lot of different parts. And that's exactly what global warming is like. And how do you address that? And we'll get to some of these areas that are highlighted. But again, if you go back to Mrs. Barnhart's class and say, stop burning stuff, that's one thing to remember. Another is how complicated it's Rubik's Cube. So now you're getting an idea here. So here's a start to the solution. This is the MIT roadmap that we put together. And we're going to cover just in the rest of the presentation, just 4 different areas, and there's a lot more than that. But we'll talk about a climate authority. We'll talk about clean electricity, transportation, and carbon capture as possible solutions here. These are not singular. They all work together, by the way. So how do we reduce CO2? Well, what we do, stop burning stuff and replace burning stuff with electricity, and then ideally some zero carbon fuels in certain applications. If we electrify, what happens to electricity demand? Well, we're going to electrify cars and trucks and school buses and houses and buildings and industry and cement making and all these things. Well, what's going to happen is electricity demand is going to go way up. And so that is part of this Rubik's Cube problem. How do we satisfy that demand? So let's just talk about transportation and some of the complexity here. The top half is fuels, the bottom half is electric vehicles, and we're going to run to the bottom half first. But let me just give you some ideas here. So by 2035, the target is to get EV cars and trucks. This is all light duty, things that we normally drive. Those would all be electric. By 2040, heavy duty trucks and buses. 2045, we're in that period. We do fuel cell locomotives, and then we do marine craft as well. And then sometime by 2050, all internal combustion engines would be off the road. Big trucks, little trucks, cars, anything that used gas or diesel off the road, other than save a couple of antique cars. So that's sort of the complexity on the EV side. Now, we're also looking at fuels because EVs don't necessarily work for all these applications. So one of the things we can do right away is begin to convert diesel engines to use biodiesel. It's fairly simple, actually. But ideally, in longer term, we'd use hydrogen in trucks and some aircraft and other transportation. So that's the goal, sort of how we're going to get there. You can see how complicated that is. Let's talk about who's buying in so far. The auto companies have bought in. So that's not the problem. I talked about technology. Auto companies have the technology, and you'll recognize Toyota, Honda, and GM, and Volvo, and so forth. School buses, and Daimler, and so forth. Everybody's bought in. Recently at the COP26 in Scotland, 200 countries signed an MOU to get what's called drive to zero in transportation by no later than 2035. So there's a widespread effort to get transportation to be zero emission. So you say, okay, zero emission, how do we get there? This time we're going to start on the right-hand side of the chart and then go left. So the vehicle goals are zero emission, tailpipe emissions, longer distance without charging, and also, however we configure this, you need to be able to maintain the speed of the vehicle and the cargo. So how do you get that done? Let's go to the left center column now. Say, we'll put in batteries. And batteries send energy to the electric motor. Batteries, however, need to be recharged. They're heavy, they take up space, but they're critical because batteries are ideal to provide large bursts of energy. You can't, accelerate a truck without a large burst of energy, or train, or let's stick with trucks. So let's go to then the far left-hand side. And how do we help the battery? The purpose of a fuel cell is to make electricity. It's a chemical reaction, so you got hydrogen or some other source of hydrogen. And the output is a steady flow of electrons. You also get water. So the fuel cell then charges a battery, so it reduces the amount of time it needs to stop to get recharged. The battery provides the power to the vehicle. Well, what can't we electrify easily? Large commercial aircraft, for one. I mean, people have talked about electric aircraft, but let's be realistic here. We're not going to fly coast to coast on an electric aircraft. It's too heavy, too much space, batteries, fuel cells. So the short-term solution is there's 100% biodiesel aviation fuel, which, if we look at experience in heavy-duty trucking, would reduce emissions about 75%, and you can use existing engines, aircraft engines, so there's no big change-out. Longer term, and this is a sort of baseline now, I don't know if anybody else has got a practical solution, but using compressed hydrogen, sort of a non-carbon jet fuel of some sort, which would result in very low or zero emissions. Mentioned hydrogen several times. How do we get hydrogen? Well, go back, there's lots of hydrogen in water, H2O. So think about maybe middle school or high school, the electrolysis when you're in chemistry class. There's electrolysis, you put a little, tie something to a battery and then put a little probe in water and the bubbles out, and that's hydrogen. That's fundamentally how it works. But we get the hydrogen out, whatever the source. It's then compressed into high-pressure tanks, and it's installed in the truck or fuel cell, wherever. And when it's burned, It makes more water. There's no carbon dioxide. Now, hydrogen, because there's so much nitrogen in the air, you get some sort of NOx emissions. There's no NOx with a fuel cell, but when you burn it, there is. There are numerous efforts to minimize NOx, which is a greenhouse gas. We're not there yet, but we're making a lot of progress. Now, let's turn to electricity. We've talked about a lot of publicity about solar and wind, and I threw gerbils down here too, but solar and wind, and are they the right answer, the only answer? So in the upper right, I repeated that electricity demand chart. Let's look at solar and wind. They're ideal because there's no carbon dioxide with either one. But the output's highly variable. Think about a sine wave here, and it's up and down. This might be exaggerated in some cases, but obviously solar doesn't work at night. Wind, if you've ever lived in the upper mid, we spent a lot of time in Michigan, and there'll be days, if not weeks at a time, when the sun's not out, and there'll be virtually no wind. So neither one of those systems would work that well. What we're faced with is the need for stable generation to avoid demand exceeding supply. So what are some other issues with renewables? Remote locations. You might need new transmission lines, for example. Solar likes to have open areas, ideal open areas, existing farmland. So society, do we want to take out farmland and put in solar? Wind turbines have regular maintenance required. That's no surprise there. The life of both solar and wind is about 25 years. There's battery storage required, and then there are, both of them are, well, particularly wind, and subject to extreme weather. And so if, like wind generators, the big ones, need the grid operating for them to operate. And so if you go back to what happened in Texas this past winter in 2021, there was basically no electricity from the wind generators because part of the system went down, the transmission system. So, why renewables might need some support? We looked at that and we're saying, gee, are they the only answer? So let's look at this. This is a chart that there's 3 bars here, and on the left-hand side, the blue part, says what's the current electricity mix, and if you said, oh, nuclear is, call it 20 just for a second, they call it 20%, and then fossil fuel, that's coal and natural gas, it's about 60, and then solar and wind renewables are about 20. Now, if you think, go to the demand in the upper left-hand corner, and I got to tell you, I think we underestimated the demand increase here, but this is an example. So what we've said is we're going to eliminate all fossil fuel going forward by some date, 2050 or whatever. So now what does that leave? Well, we have nuclear. Some people want to eliminate that. And so now you got solar and wind. There's some geothermal and all that, but it's a fraction of what we need. So you look at this chart and you say, what do we do here? So the potential problem is this. The base load demand, or what goes on all the time, requires a constant source of electricity. So that's heating the house, buildings, now charging the car. That needs to be there all the time. Sometimes there's peak load demand, which we can manage with natural gas, but we're taking away gas as well. So if the base load demand is going to go up dramatically. Now, if we don't meet that base load demand, then let's pretend we've now electrified transportation, as we talked about. So, okay, we've got a limited amount of fuel left in the vehicle. And if there's a catastrophic event for some reason, you can't just drive off someplace and deliver things like you can now, that we face a shutdown or a slowdown. So let's recognize that wind and solar, the output's highly variable. And also, frankly, the battery storage, no matter how much we put into it, is likely to be inadequate to really handle an interruption or a strong baseload demand over time. So, what do we do? Well, now I'm going to tell you this is controversial, and I'm not saying everybody's bought in, but I just want to give you some facts. Let's look at the land area required by solar. That's in yellow on the left-hand side. So that's for roughly 1,000 megawatt output, which is 400,000 to 500,000 homes in the south. In the north, you'd get a few more homes than that, but we'll just call it 1,000 megawatts right now. So the yellow represents the area for solar. That's existing technology, and it over time might be a little less, but that's where we are. On the right-hand side, the blue is wind. Now, granted, wind, these are wind generators, so the ground is not affected, but you got, this is the coverage for wind, okay? And you got transmission lines and all that connected with it. That's the area. Now, in the lower right of each chart is a dark blue area, which represents a nuclear plant of the same megawatt output in the same area. That's for the plant and all the surrounding area. So you look at that and you say, I need all this space for both wind and solar, and we've got this nuclear plant. So, should nuclear be part of the mix? On the negative side, nuclear is perceived as risky, especially if there's a serious event, and that's true. There's also serious events with, we had an oil spill in the Gulf a few years ago. So it's different kind of risk, but nonetheless, any kind of fuel, there's some risk involved. Okay, then what do we do? Where do we store the spent fuel? I mean, clearly the half-life is a long time. So as bad as the CO2 is, the life of nuclear fuel is longer. New plants are costly compared to new wind and solar. So there's an economic issue on new. There's widespread resistance to nuclear plants, not in my backyard, and they do require water for operation. On the positive side, so this is what we're trying to do, is balance this. It's ideal for constant electricity output. Now, they talked about base load demand, and they're perfect for that. They go all the time. There's zero CO2, another greenhouse gas. The facilities last longer than solar or wind, 50, 60 years in many cases. If you take an existing facility, not a new facility, part of the cost is all the permits and so forth, but the cost per kilowatt hour is low. You use existing transmission lines. There's a whole sort of genre of new designs that are smaller, safer, using the heat that currently escapes, using it for other purposes. And as we saw in the previous slide, nuclear has a significantly smaller footprint than solar or wind. So there's another technology that people talk about, and they say, well, this is the solution. Is carbon capture the silver bullet? So the graphic is, the little guy chasing the CO2 butterfly, as it were. But let's talk about carbon capture, also known as sequestration. What we're doing is trying to capture, it's a little less than 500 right now, but let's call it 500 parts per million. So that's not very much. So you end up capturing lots of air. Now, if you put it on a plant like a power plant, coal plant, obviously the concentration is much higher. But if you just normal atmosphere, the approach is very energy intense and expensive. That's existing technology. There's some work on it, but we're not there yet. Storing CO2, so where do you store it? Gas has a tendency to escape over time. So, then it goes back in the atmosphere. So now there's also an effort to convert CO2 to fuel. Okay, you still have carbon. What do you do with that? So what's left? We referenced this earlier to reach the 2050 target. We just run over the technology, highlight of that. But now let's talk more about education and adoption of the technology and how are we going to get this stuff implemented. So who should be educated about all these solutions? Well, clearly Congress. Then we've got, I put the lobbyists down there as well. But you have the media. I mean, they're critical in conveying the message. You've got Wall Street, Main Streets, business people. Then you have the general public, and then a lot of emphasis on schools. And the reason for that is people under age 30 will be the most affected by this. And so we've got to get them educated about the causes and the solutions. A policy issue, what's the best path to zero emissions? Some people say market forces. There's also discussion of mandates. So let's look at market forces for a second. There's clearly support among a percentage of business people who resist change. Now, they just don't want government intervention. There's also a percentage of the population that feels that way. And clearly, market forces would reduce government subsidies and costs, at least direct costs. They might be different with taxes, but clearly direct costs. So what are the negatives with market forces? Well, frankly, the one is you'll never achieve or will never achieve zero emission goals. I have to tell you, I have spent a lot of time going through all this. And when we finish the slide, if you've got a better idea of a practical solution, please let us know. But spend some serious time thinking about it, because I don't frankly know if there's another solution. But okay, we talk about never achieve. Why? Well, look at the state resistance to vaccines, EPA, and other efforts. In addition, market forces allow the wealthy to buy their way out, and they can continue to burn fossil fuel. So is that fair? The mandates appear to be the only option. So what the mandate would do in some fashion is restrict fossil fuel consumption. I think it also should include, implementation of the Defense Production Act to ensure there's adequate availability of electric products and electricity. We saw earlier that, demand, we're not sure on how we're going to meet all the demand, so we've got to address that as well. And it also might include possible rationing of items. I know that probably gets some people upset, but at least think about it. So we recommended the mandate. So how are we going to pull that off? And we spent a lot of time, and I will tell you, not everybody in the MIT group agrees with this, but this is where we are. We would set up some sort of climate action authority. It would be a single federal agency to coordinate all this. And the reason for that, the U.S. needs a cohesive, focused plan. There's a short time to develop that and implement it. And if we have the federal agencies, each one of them do it, it's much like the states. Everybody's going to have their own way of doing it. So here's the overall plan, and then you, DOT or NASA or whomever, you go implement however you need to satisfy your mission, but it needs to be consistent with the overall plan. The agency needs protection, and this might be the most difficult part. The agency needs protection from changes in administrations, presidential whims, and congressional meddling. I think the public needs to sort of stand up together and say, if we, as we go forward here, people begin to realize the severity of the situation, is that no meddling, guys. Here's the plan. Go do something else. Cost of all this is high, but I guess we have to look at it from two ways. One, no investment is very risky. We saw earlier that do nothing and it's goodbye planet. But what we have is increased severe weather, more droughts. I put roulette wheel here. I think that's being very generous. The risk is much worse than that. You have more droughts, forest fires, more intense hurricanes, crop damage, food shortages. Oceans continue to rise. Goodbye a lot of coastal cities, and goodbye Outer Banks, North Carolina. More threats to national security, and a likely uninhabitable planet. So with investment, there's far less risk. It's not 100%, far less risk. Less frequent catastrophic weather events. Actually, the cost is lower than it would be to wait. Significant economic growth. Every time we've had a major technological change, we've had economic growth, job creation. In addition, coastal cities will survive, and we should have a livable planet for future generations. So how can you help save the planet? Well, go back to World War II. I mentioned that as a reference point, but, we can do it together. Uncle Sam wants you. We can do it together. But get personally involved. As I mentioned, we had quite a few disciplines within the MIT group. But believe me, we need more. We're heavily science and quantitatively based. But so we leverage everyone's educational and work experience. Could work with schools, 501c3s, religious groups. There's a way to become an affiliate of this MIT program, or the MIT Alumni for Climate Action. MACA is our acronym. There's some educational tools available on the website, and you could become a good example. So I think also when we go through this, there's a lot of effort on social justice, and I phrased it this way: ensuring that climate change solutions are equitable. And I've referenced World War II a couple of times, and I think that's important. I know none of us around in World War II are highly likely, but everyone was affected. It wasn't that, oh yes, well, Kansas or Arkansas, it doesn't matter what state, said, no, we're not going to send our guys to the draft. No, son, you don't seem to understand. But everyone was affected. Everyone participated. We'll save the in-law stories, but father and son of my father-in-law and his father enlisted the same day, okay, shortly after Pearl Harbor. A long-term perspective then, people recognized that the sacrifices were temporary. There was rationing, it was across all groups. But people said, okay, we're going to sacrifice. But there were a lot of new jobs created and across all economic groups. What we need to do is ensure there's equitable solutions. So the Earth's temperature affects everybody. We've got to eliminate whatever these solutions are, and that's why I keep going back to mandates, eliminate the way to buy out. And so if we have some sort of payment, which is probably necessary for certain things, we need to make sure that those payments aren't linked to, gee, this person paid higher taxes, therefore they get a higher payment. No. It's more based on need, and I know that bothers some people, but it needs to be based more on need than income. Okay, and I put down here, and again, this might be a bit controversial, but conscription for climate programs. If we had, say, a 2-year conscription program, it would ensure everyone served. It would help build skills, particularly with younger people. Don't ask me what age yet, we haven't gone through all this, but help build skills for the post-government service. And it also builds cross-economic strata relationships. For those of you who did not serve in the military, that is a great place to meet and work with people that you would never meet or work with otherwise. So I think in terms of breaking down the barriers and getting at the real problems that we have right now and what needs to be addressed for climate change, conscription of some sort might be an interesting way of doing it. Part of it, I'm not saying the whole thing. Okay, I mentioned your own carbon footprint. There's a calculator, EPA calculator. I encourage you to look at that. It's based on zip code, which electricity mix, and then it asks for what's your home heating, whether it's gas or electricity or oil, which is still around New England. What's your consumption for gas or whatever, and electricity usage, transportation. Also talks about waste disposal. How do you dispose of food and various packages? But go on that EPA site or just Google EPA carbon footprint. Okay, that's it. There's a couple Q&A after that. I hang around, but if you need to go, thanks very much for your time. If you have questions, comments, go on the MIT website. There's an affiliate program. You can join our group. You don't need to be an MIT alum to do that, but it's the MIT Alum, and then the number 4, climate.org. And also, my contact information is at the bottom. Feel free to email me, and I'll try to get back with you. So, a couple more. If you got another 2 minutes, hang around. We're at 45 minutes right now. Okay, you might have a couple of other questions. Excuse me. So, a number of people have asked, if we get to zero emissions by 2050, will the Earth's temperature start to cool right away? And the answer is no. Go back to that slide that, how long does greenhouse gas last? And just take the CO2, and that's 100 years. So the temperature is likely to rise for the next 50 years, although much more slowly. And then it should start to decline. But if we don't do 2050 with zero, we keep pushing out when it's going to start to decline. So another question is, will the carbon tax help? The answer is yes, it'll help. But it won't result in a zero carbon economy by 2050. It's okay to put it in now. We've got to figure out how to redistribute it. But again, that's a market force. And if you've got enough money, you buy your way out. And this is not a program where you can buy your way out. Another one, can we just plant more trees? The answer is yeah. Plant as many trees as we want. Trees clearly absorb CO2. On the other hand, when they release CO2 when they die or are burned. So we need to realize that. They're slow growing, but absolutely, that's one of the things you can do is plant more trees. Another question is, why should the U.S. do anything if China doesn't? If we're to lead, we need to do our part first. Now, there's a lot of progress, and I know there's a lot of controversy on this, and there's a lot more detail, but if we look at China has made significant progress in some areas, in fact, in some areas more than the U.S., but we've all got to do our part. So the U.S., if it wants to have moral leadership, needs to lead. So, yes, do our part, talk to China. If they don't cooperate, I think economic sanctions might stimulate them. So finally, there's a lot more questions, but we'll stop there. Want to learn more about the impact of the proposed solutions? There's a great program called En-ROADS, E-E-N-R-O-A-D-S. It was originally developed at MIT. And it's an interactive model. You can do it online. It's designed for multi-skill levels. You don't need to be an expert in computers. If you just know how to get on one and move the cursor back and forth, you're okay. But what it does, it measures the impact of specific recommended solutions. So if you say, let's go back to the trees. If we plant more trees, what happens to the Earth's temperature? And then it provides an estimate of that. If we electrify everybody's house, what does that do? So it's an ideal tool for group learning. There's another version of that where you can negotiate. But I would highly recommend looking at that. Again, Google that. A couple of different ways to make it happen. There's a YouTube. There's a link right on this slide at the bottom. But if you can't see it, just Google En-ROADS on YouTube. And you'll get some idea of what it's about. Well, anyway, that's the end of it right now. But thanks again for your time. Feel free to contact the group or contact me. But I very much appreciate you're taking time to listen.